In organic chemistry, the term aromaticity is used to describe a cyclic, planar molecule with a ring of resonance bonds that exhibits more stability than other geometric or connective arrangements with the same set of atoms. Aromatic molecules are very stable and do not easily break apart and react with other substances. Organic compounds that are not aromatic are classified as aliphatic compounds. They might be cyclic, but only aromatic rings have special stability. Since the most common aromatic compounds are derivatives of benzene, the word aromatic occasionally refers informally to benzene derivatives, and so it was first defined. Nevertheless, many non-benzene aromatic compounds exist in living organisms. For example, the most common aromatic rings are the double-ringed bases in RNA and DNA. An aromatic functional group or other substituent is called an aryl group. The earliest use of the term aromatic was in an article by August Wilhelm Hofmann in 1855. Hofmann used the term for a class of benzene compounds, many of which have odors, unlike pure saturated hydrocarbons. Aromaticity as a chemical property bears no general relationship with the olfactory properties of such compounds, although in 1855, before the structure of benzene or organic compounds was understood, chemists like Hofmann were beginning to understand that odoriferous molecules from plants, such as terpenes, had chemical properties that we recognize today are similar to unsaturated petroleum hydrocarbons like benzene. In terms of the electronic nature of the molecule, aromaticity describes a conjugated system often made of alternating single and double bonds in a ring. This configuration allows for the electrons in the molecule's pi system to be delocalized around the ring, increasing the molecule's stability. The molecule cannot be represented by one structure, but rather a resonance hybrid of different structures, such as with the two resonance structures of benzene. These molecules cannot be found in either one of these representations, with the longer single bonds in one location and the shorter double bond in another. Rather, the molecule exhibits bond lengths in between those of single and double bonds. This commonly seen model of aromatic rings, namely the idea that benzene was formed from a six-membered carbon ring with alternating single and double bonds, was developed by August Kekulé. The model for benzene consists of two resonance forms, which corresponds to the double and single bonds superimposing to produce 6 1.5 bonds. Benzene is a more stable molecule than would be expected without accounting for charge delocalization theory, as is standard for resonance diagrams. The use of a double-headed arrow indicates the two structures are not distinct entities but merely hypothetical possibilities. Neither is an accurate representation of the actual compound, which is best represented by a hybrid of these structures, as can be seen at right. AC equals C bond is shorter than AC minus C bond, but benzene is perfectly hexagonal. All 6 carbon-carbon bonds have the same length, intermediate between that of a single and that of a double bond. In a cyclic molecule with 3 alternating double bonds, cyclohexatrene, the bond length of the single bond would be 1.54 A and that of the double bond would be 1.34 A. However, in a molecule of benzene, the length of each of the bonds is 1.4 A between these two lengths. A better representation is that of the circular pi bond, in which the electron density is evenly distributed through pi bond above and below the ring. This model more correctly represents the location of electron density within the aromatic ring. The single bonds are formed from overlap of hybridized atomic sp2 orbitals in line between the carbon nuclei. These are called sigma bonds. Double bonds consist of a sigma bond and a pi bond. The pi bonds are formed from overlap of atomic p orbitals above and below the plane of the ring. The following diagram shows the positions of these p orbitals. Since they are out of the plane of the atoms, these orbitals can interact with each other freely, and become delocalized. This means that, instead of being tied to one atom of carbon, each electron is shared by all 6 in the ring. Thus, there are not enough electrons to form double bonds on all the carbon atoms, but the extra electrons strengthen all of the bonds on the ring equally. The resulting molecular orbital is considered to have pi symmetry. History. The term aromatic, the first known use of the word aromatic as a chemical term, namely, to apply to compounds that contain the phenyl radical, occurs in an article by August Wilhelm Hofmann in 1855. If this is indeed the earliest introduction of the term, it is curious that Hofmann says nothing about why he introduced an adjective indicating olfactory character to apply to a group of chemical substances, only some of which have notable aromas. Also, many of the most odoriferous organic substances known are terpenes, which are not aromatic in the chemical sense, but terpenes and benzenoid substances to have a chemical characteristic in common, namely higher unsaturation than many aliphatic compounds, and Hofmann may not have been making a distinction between the two categories. Many of the earliest known examples of aromatic compounds, such as benzene and toluene, have distinctive pleasant smells. This property led to the term aromatic for this class of compounds, and hence the term aromaticity for the eventually discovered electronic property. The structure of the benzene ring in the 19th century, chemists found it puzzling that benzene could be so unreactive toward addition reactions, given its presumed high degree of unsaturation. The cyclohexatrene structure for benzene was first proposed by August Kekulé in 1865. Most chemists were quick to accept this structure, since it accounted for most of the known isomeric relationships of aromatic chemistry. The hexagonal structure explains why only one isomer of benzene exists and why di-substituted compounds have 3 isomers. Between 1897 and 1906, J. Thomson, the discoverer of the electron, proposed 3 equivalent electrons between each pair of carbon atoms in benzene. An explanation for the exceptional stability of benzene is conventionally attributed to Sir Robert Robinson, who was apparently the first to coin the term aromatic sextet as a group of 6 electrons that resists disruption. In fact, this concept can be traced further back, via Ernest Crocker in 1922, to Henry Edward Armstrong, who in 1890 wrote, "The centric affinities act within a cycle. Benzene may be represented by a double ring, and when an additive compound is formed, the inner cycle of affinity suffers disruption. The contiguous carbon atoms to which nothing has been attached of necessity acquire the ethylenic condition." Here, Armstrong is describing at least 4 modern concepts. First, his affinity is better known nowadays as the electron, which was to be discovered only 7 years later by J. Thomson. Second, he is describing electrophilic aromatic substitution, proceeding through a Wieland intermediate, in which the conjugation of the ring is broken. He introduced the symbol C centered on the ring as a shorthand for the inner cycle, thus anticipating Eric Clark's notation. It is argued that he also anticipated the nature of wave mechanics, since he recognized that his affinities had direction, not in merely being point particles, and collectively having a distribution that could be altered by introducing substituents onto the benzene ring. The quantum mechanical origins of this stability, or aromaticity, were first modeled by Huckel in 1931. He was the first to separate the bonding electrons into sigma and pi electrons. Aromaticity of an arbitrary aromatic compound can be measured quantitatively by the nucleus-independent chemical shift computational method and aromaticity percentage methods. Characteristics of aromatic compounds. An aromatic compound contains a set of covalently bound atoms with specific characteristics. A delocalized conjugated pi system, most commonly an arrangement of alternating single and double bonds. Coplanar structure, with all the contributing atoms in the same plane. Contributing atoms arranged in one or more rings. A number of bidelocalized electrons that is even, but not a multiple of 4. That is, 4n plus 2 pi electrons, where n equals 0, 1, 2, 3, and so on. This is known as Huckel's rule. According to Huckel's rule, if a molecule has 4n plus 2 pi electrons, it is aromatic, but if it has 4n pi electrons and has characteristics 1 to 3 above, the molecule is said to be anti-aromatic. Whereas benzene is aromatic, cyclobutadiene is anti-aromatic, since the number of bidelocalized electrons is 4, which of course is a multiple of 4. The cyclobutadiene ion, however, is aromatic. An atom in an aromatic system can have other electrons that are not part of the system, and are therefore ignored for the 4n plus 2 rule. In furan, the oxygen atom is sp2 hybridized. One lone pair is in the pi system and the other in the plane of the ring. There are 6 pi electrons, so furan is aromatic. Aromatic molecules typically display enhanced chemical stability, compared to similar non-aromatic molecules. A molecule that can be aromatic will tend to change toward aromaticity, and the added stability changes the chemistry of the molecule. Aromatic compounds undergo electrophilic aromatic substitution and nucleophilic aromatic substitution reactions, but not electrophilic addition reactions as happens with carbon-carbon double bonds. The circulating pi electrons in an aromatic molecule produce ring currents that oppose the applied magnetic field in NMR. The NMR signal of protons in the plane of an aromatic ring are shifted substantially further downfield than those on non-aromatic sp2 carbons. This is an important way of detecting aromaticity. By the same mechanism, the signals of protons located near the ring axis are shifted upfield. Aromatic molecules are able to interact with each other in so-called pi-pi stacking. The pi systems form 2 parallel rings overlap in their face-to-face orientation. Aromatic molecules are also able to interact with each other in an edge-to-face orientation. The slight positive charge of the substituents on the ring atoms of one molecule are attracted to the slight negative charge of the aromatic system on another molecule. Planar monocyclic molecules containing 4n pi electrons are called anti-aromatic and are, in general, unstable. Molecules that could be anti-aromatic will tend to change from this electronic conformation, thereby becoming non-aromatic. For example, cyclooctatetran distorts out of planarity, breaking pi overlap between adjacent double bonds. Recent studies have determined that cyclobutadiene adopts an asymmetric rectangular configuration in which single and double bonds indeed alternate. With no resonance, the single bonds are markedly longer than the double bonds, producing unfavorable p-orbital overlap. This reduction of symmetry lifts the degeneracy of the 2 formerly non-bonding molecular orbitals, which by Hund's rule forces the 2 unpaired electrons into a new, weakly bonding orbital. Hence, cyclobutadiene is non-aromatic. The strain of the asymmetric configuration outweighs the anti-aromatic destabilization that would affect the symmetric square configuration. Importance of aromatic compounds. Aromatic compounds play key roles in the biochemistry of all living things. The 4 aromatic amino acids histidine, phenylalanine, tryptophan, and tyrosine each serve as one of the 20 basic building blocks of proteins. Further, all 5 nucleotides that make up the sequence of the genetic code in DNA and RNA are aromatic purines or pyrimidines. The molecule heme contains an aromatic system with 22 pi electrons. Chlorophyll also has a similar aromatic system. Aromatic compounds are important in industry. Key aromatic hydrocarbons of commercial interest are benzene, toluene, orthoxylene and paraxylene. About 35 million tons are produced worldwide every year. They are extracted from complex mixtures obtained by the refining of oil or by distillation of coal tar, and are used to produce a range of important chemicals and polymers, including styrene, phenol, aniline, polyester and nylon. Types of aromatic compounds. The overwhelming majority of aromatic compounds are compounds of carbon, but they need not be hydrocarbons. Neutral homocyclics, benzene, as well as most other anilines with the formula CnH and where N is an even number, such as cyclotetradecahetane. Heterocyclics. In heterocyclic aromatics, one or more of the atoms in the aromatic ring is of an element other than carbon. This can lessen the ring's aromaticity, and thus increase its reactivity. Other examples include pyridine, pyrazine, imidazole, pyrazole, oxazole, thiophene, and the benzanulated analogues. In all these examples, the number of pi electrons is 6, due to the pi electrons from the double bonds as well as the 2 electrons from any lone pair that is in the p orbital that is in the plane of the aromatic pi system. For example, in pyridine, the 5 sp2 hybridized carbons each have a p orbital that is perpendicular to the plane of the ring, and each of these p orbitals contains 1 pi electron. Additionally, the nitrogen atom is also sp2 hybridized and has 1 electron in a p orbital, which adds up to 6 p electrons, thus making pyridine aromatic. The lone pair on the nitrogen is not part of the aromatic pi system. Pyrrole and imidazole are both 5-membered aromatic rings that contain heteroatoms. In pyrrole, each of the 4 sp2 hybridized carbons contributes 1 pi electron, and the nitrogen atom is also sp2 hybridized and contributes 2 pi electrons from its lone pair, which occupies a p orbital. In imidazole, both nitrogens are sp2 hybridized. The one in the double bond contributes 1 electron, and the one which is not in the double bond and is in a lone pair contributes 2 electrons to the pi system. Fused aromatics and polycyclics. Polycyclic aromatic hydrocarbons are molecules containing 2 or more simple aromatic rings fused together by sharing 2 neighboring carbon atoms. Examples are naphthalene, anthracene, and phenanthrene. In fused aromatics, not all carbon-carbon bonds are necessarily equivalent, as the electrons are not delocalized over the entire molecule. The aromaticity of these molecules can be explained using their orbital picture. Like benzene and other monocyclic aromatic molecules, polycyclics have a cyclic conjugated pi system with p orbital overlap above and below the plane of the ring. Substituted aromatics. Many chemical compounds are aromatic rings with other functional groups attached. Examples include trinitrotoluene, acetyl salicylic acid, paracetamol, and the nucleotides of DNA. Aromatic ions. Aromatic molecules need not be neutral molecules. Ions that satisfy Huckel's rule of 4n plus 2 pi electrons in a planar, cyclic, conjugate conjugated molecule are considered to be aromatic ions. For example, the cyclopentadienyl anion and the cycloheptatrienylyl cation are both considered to be aromatic ions, and the azulylene molecule can be approximated as a combination of both. In order to convert the atom from sp3 to sp2, a carbocation, carbanion, or carbon radical must be formed. These leave sp2 hybridized carbons that can partake in the pi system of an aromatic molecule. Like neutral aromatic compounds, these compounds are stable and form easily. The cyclopentadienyl anion is formed very easily, and thus 1,3-cyclopentadiene is a very acidic hydrocarbon with a pKa of 16. Other examples of aromatic ions include the cyclopropenium cation and cyclooctatetraenyl dianion. Atypical aromatic compounds. Aromaticity also occurs in compounds that are not carbocyclic or heterocyclic. Inorganic six-membered ring compounds analogous to benzene have been synthesized. For example, borazine is a six-membered ring composed of alternating boron and nitrogen atoms, each with one hydrogen attached. It has a delocalized pi system and undergoes electrophilic substitution reactions appropriate to aromatic rings rather than reactions expected of non-aromatic molecules. Quite recently, the aromaticity of planar C6-5 rings occurring in the zintalphase lithium silicide was experimentally evinced by Li solid-state NMR. Metal aromaticity is believed to exist in certain clusters of aluminium. For example, Homo Aromaticity is the term used to describe systems where conjugation is interrupted by a single sp3 hybridized carbon atom. Moebius Aromaticity occurs when a cyclic system of molecular orbitals, formed from p atomic orbitals and populated in a closed shell by 4n electrons, is given a single half-twist to form a Moebius strip. A pi system with 4n electrons in a flat ring would be anti-aromatic, and therefore highly unstable, due to the symmetry of the combinations of p atomic orbitals. By twisting the ring, the symmetry of the system changes and becomes allowed. Because the twist can be left-handed or right-handed, the resulting Moebius aromatics are disymmetric achiral. But as of 2012, no Moebius aromatic molecules had been synthesized. Aromatics with two half-twists corresponding to the paradromic topologies were first suggested by Johann Listing. In carbobenzene, the ring bonds are extended with alkene and alene groups. Why aromaticity is a concept developed to explain the extraordinary stability and high basicity of the guanidinium cation. Guanidinium is not a ring molecule, and is cross-conjugated rather than a linear pi system, but is reported to have its 6 pi electrons delocalized over the whole molecule. The concept is controversial and some authors emphasize different effects.